Swayam Prabha. Digital India. Educated India.
So, let us start this lecture with a thought process from Suze Orman. When you are grateful, that means when you can see what you are, you unlock the blessings to flow into your life, right. That means basically what is trying to say, an attitude of gratitude, helps you to get the blessings flowing into your life. So, that is the things what he is saying, and which is there in our scriptures as well. So, let us now look at, in the last lecture we basically derived the equation for energy or the heat, and then later on I summarize those equations for steady flow process, and then club this continuity equation into the momentum, species and energy. All I have done, okay. I did not tell in the last lecture, but we have done. Are you getting? That means continuity is already being taken care of by that, and in the sense using the continuity we have neglected those terms and then simplify the equation. And today I will be just touching upon little bit about boundary layer, and if you look at, we are considering a flow over a flat plate, right. You might be wondering that where the combustion will be taking place, flow over a flat plate, is it possible? No, certainly no. But however, whenever you will be looking at flow over a solid propellant, or combustion over a solid propellant, or a wood combustion, right, we can consider the flow over a solid surface, and that you can consider as a not a flat plate, but however if I will take a wood, let us say there is a ply board. Nowadays we are using ply board, right, in our door and other things. So, there is a combustion, there is a fire, what will happen? The flow will be taking place, something like that. Or let us say your bench, now there is a start burning, then some flow will be taking place, of course, which will be natural convection, and keep in mind that natural convection will be using the gravity. The gravity what we consider, that is very important in the flow due to natural combustion, natural convection, right. And what is happening here, that if you look at in this, which already you might have studied, these are the laminar flow, there is a transition regime, like there will be some disturbances, there will be also turbulent flow, and there will be laminar sublayers, and keep in mind that velocity profile for the laminar and turbulent is different. So, what do you mean by turbulent, right? We will be seeing little bit later on, and how we can define. Can you define the turbulent flow or not? You can define, right? Okay, we will discuss that, whether you can define or not. So, what is happening here, the velocity profile, it is increasing, because at this solid surface, if you look at, what will be the condition here, the Vx will be 0, right. In this place Vx will be 0, and V along the y direction, if I say this is y at the solid surface, Vx and Vy will be 0, that is known as no slip condition, and that will be valid for what? Not only Newtonian fluid, but also for continuum. When non-Newtonian fluid, it will be true also, but continuum concept, Knudsen number, right. If I go rarefied gas, that is not true, okay. So, therefore, most of the flow what we will be considering is basically coming under continuum. So, therefore, we will be using no slip conditions. and keep in mind that this region is basically known as viscous region, right, and this region will be inviscid flow, right, there the viscosity term will be neglected, and this portion is basically known as, you will look at this portion is boundary layer, and boundary layer thickness you can define as what, the wherever this is the velocity v infinity, wherever it will get into 99 point of the stream velocity, right, and keep in mind this is little exaggerated velocity profile, it is not drawn properly. So, in principle it should be like that. If I draw a velocity profile like this, then my boundary layer will be, if it is v infinity, boundary layer will be somewhere here, this is my boundary layer, you can say, because where thickness, this is boundary layer where the v is equal to 0.99 of v infinity. Keep in mind that boundary layer thickness can be defined different way, like momentum boundary layer thickness, right, and this is known as the velocity boundary layer thickness. So, wall friction is very important here, and viscosity terms has to be used. And if I look at incompressible fluid, of course, we need not to consider that, but keep in mind that this mass conservation, like dvx by dx dvy by 0, and this is the equation what we have already talked about it, and we are not considering the gravitational effect here. And for the boundary layer approximation, Vx is very greater than the Vy. Vy along the y direction is very small, right, and the gradient dvx by dx will be far greater than the dvx by dy and dvy by dy and dv by dx. So, therefore, these terms will be neglected, like these terms can be neglected here, and what will say, this is the basically x momentum and this is y momentum, right, and y momentum there will be some approximation, it will be turns out to be. So, with this approximation you will get the momentum equation, basically dou p by dou y is equal to 0. What it says that along the boundary layer, right, if you look at, this is my boundary layer and we are considering laminar flow only, right, what is saying, the pressure along with this direction will be, if I say this is my x, this is y, that is remaining constant, it is not changing along the y direction at any point of x, right, that is the meaning of this. That means pressure is not a function of y, pressure is remaining constant. So, with this you can approximate this thing, and this will be mu, right, mu we are taking out is not a function of that, I am taking out. So, this will be the equation which you need to solve, and then you can get these solutions, and also you can derive a relation by delta by x pi by root over Re x, and Re is basically rho v x by what you call rho v x by mu, right, x is your distance at which you are considering the Reynolds number, right, Reynolds number will be changing along with the x direction if you are considering a boundary layer. Similarly, drag coefficient you can find out using basically tau of the wall, this is the shear stress at the wall, right, and which is when you integrate this you will get this 1.328 root over REL, and keep in mind that this L is the length here, if I consider this is my length L at which I am considering the drag coefficient for the laminar flow, right, and B is your width whatever it is considered which is perpendicular to that. So, now what we will be considering basically we will be looking at the species equation and considering a one dimensional flow, right, and in that what we will be considering is basically a one dimensional flow. Let us say in this is the one dimensional flow is taking place, and with the species it can be yi, it can be fuel, it can be oxidizer, right, which is moving along the x direction, right, with the species. And there is a we are considering one dimensional steady flow, right, for our consideration, and let us consider right single step chemistry, right. Let us consider single step chemistry, that is fuel is reacting with new moles of oxidizer going to the product of 1 plus nu. I can say rather I would put a 1 kg of fuel is reacting with nu kg of oxidizer getting into product of 1 plus nu kg of product, right. And if you look at the continuity equation, if you want to write continuity, what it would be for one dimensional steady flow, right, one dimensional, oh my god, one dimensional steady flow, what it would be? It will be rho Vx y dx is equal to 0, right, and species equation for, right, we will be writing for fuel, let us say species equations, right, for fuel, what it would be? Vx by dx is 0. I can write down d rho Vx yf dx is equal to dx rho yf right, and d is your diffusivity, right, this is your diffusivity, mass diffusivity or molecular diffusivity, plus what it will be, right. Similarly, for oxidizer I can write down rho Vx y oxidizer plus m dot triple dash oxidizer, and for product the similar equations, right. Right, I can say this is my basically equation 1 I can say, and this is my equation 2, this is 3, this is 4, this is 5. And we will consider, basically we can apply the law of mass action for equation 1. We can apply law of mass action for equation for reaction 1, basically that is single step reaction 1. We can write down that as F, this will be minus is equal to minus O oxidizer by nu and is equal to product nu plus 1. Right, let us say this is equation 6, and from this I can write down as basically I can write down m dot triple dash F plus triple dash product by nu plus 1, right, is equal to 0. Yes or no? Can I write down from this equation 6? From equation 6, because I am taking this that side, right, and that will be nothing but your 0, right. Similarly, I can write down as what you call, I can write out m dot F minus this as I can write down also F minus nu is 0, right. That is that we will not be using, I am just trying to make it, but what I will be using is this one, this is I am saying 7, this is very important equation. And why we are doing this thing? Basically we want to eliminate the source term from the equation, right. Are you getting? Because source term is causing the problem, it is arrhenius form, and then like it will be e power to the e by r u t, and then other things pre-exponential factors, right. What we will do, and we can use this equation 2 and 3, right, and I can write down in which form? I can write down as m dot triple dash, I can say, right, into dy f by dx. Can I write down? Because m dot is nothing but your rho v x. So, what I will do? I will take this and rho v x, this is this term. What is this term? I can write down as rho v x dy f by dx. Yes or no? And rho v x is nothing but your mass flux, right. This is the term. So, similarly, I can write down here as y oxidizer dx. We did in the last lecture, okay, in the similar way. Yes or no, right. Now, I will add equation 3 and 5. I will add equation 3 and 5. I am going to the next slide now, right. By adding equation 3 and equation 5, we can have, that is, I can take this out, this is a mass flux, right, dx yf plus 1 by nu plus 1 pr ypr, okay, is equal to by dx rho d. Keep in mind that diffusivity is same for all, that I am assuming, okay, it need not to be, this is an assumption, right. That means diffusivity of fuel with respect to other mixtures, other species need not to be same. If the product with respect to other species or the other mixtures need not to same, I am taking considering same, that you keep in mind, right. Otherwise I cannot, okay. This is an approximation, right, by dx yf plus ypr divided by nu plus 1 is equal to f plus product divided by nu plus 1, and by equation 7 this is 0 as per equation 7. And what is this term? Can you recall yf plus 1 over nu plus 1 ypr? Can you recall? This is nothing but your mass fraction, which I had discussed where in the when we had discussed thermodynamics, right, equivalence ratio and then mass fraction, okay. As we know that yf plus 1 by nu plus 1 ypr is nothing but your mf, mass fraction, right. So, therefore, I can write down, if I say this is equation 8, can I say this equation 8, right? Can I say this equation 8? Just look at it. So, then I can write by using the definition of mass fraction, equation 8 becomes mf, right, equal to dx rho d by dx mf. So, this is the equation, right. I can also write down as, maybe this is better, I can write down this minus, I am just writing, that is all, taking the to the left hand side, nothing else I am doing, is equal to 0, and this equation is known as the mixture fraction equation, right. This is known as mixture fraction governing equation for one dimensional flow, okay. For two dimensional flow you can also do that. I have just taken simplified form, and keep in mind that this mixture fraction is basically a conserved scalar, and important thing is that, like, the source term is not there, right. The source, that means equation 9 is a sourceless, which is nonlinear in nature, which indicates conservation of species, right. Because if you look at, this is the convection term and this is the thing, and this mf, is the same, is like a property, right. You now we are getting, this is basically a variable, it can be used as a variable and which is conserved, is not it? Like the way species is conserved, momentum is conserved, right, but it is scalar, it is not a vector. Are you getting a point? So, therefore, this is the things which we will stop over here, and we will be using this mixture fraction equation particularly when we are dealing with the jet diffusion flame, right. I may not consider for droplet combustion, but droplet combustion also it can be utilized, particularly when there is a diffusion flame, right. This is being used very much. If you recall, when I had discussed about mixture fraction, I had told you this is meant for only for diffusion flame, not for premix, right, because the meaning will be not having any sense if we use for the premix flame. Thank you very much.